So you can notice that if you put this in here, if you look at the graph of cosine, cosine looks like that, something like that. And if you look at the area from 0 to 2 pi, you're looking at that area in there. If you evaluate this, you can evaluate this as using that integral evaluation formula. Right? It says use any antiderivative of cosine and evaluate it for those two and subtract it, right? So what's an antiderivative for cosine? Sine, right? So you could do sine x evaluated for pi over 2 and take away that evaluated for 0. So if you do sine of pi over 2 minus sine of 0, sine of 0 is 0. Sine of pi over 2 is 1. 1 minus 0, it's 1. This area underneath here is 1. If you do this one you can do without, you should be able to use some geometry and understanding if you have even or odd functions. This thing's an even function. The graph looks like that. Now if I was to draw it properly, it's going to be 2, right? Because this, again, if I was to draw it properly, that should equal that, right? So this should be 2, and that area in there should be 2. If you do the same thing here and you do sine x evaluated for, sine x evaluated for, all kinds of problems here, circle bracket, pi over 2, negative pi over 2, right? Evaluate it between those two values. Here you get 1 sine of pi over 2 minus negative 1, which is 2. You have to, sometimes people make mistakes on the grade 8 stuff, right? The sign errors and stuff like that. So make sure you're watching carefully. This one, we start to think about what happens here with negative areas. I don't know if you did this one and saw what happened, but if you draw the graph of sine, something like that, you have between negative pi over 2 and pi over 2, so between here and here, well, it looks like, that area, just because of symmetry with the cosine graph, what should that area be? It's the same shape. It should be 1, right? What should this be? Well, yeah, we're going to call this negative 1. Negative 1, 1. Area below the axis is going to be negative area. Okay, area below is considered negative. When we look at real applications of this, that's going to be important to realize. Okay, if you evaluated this for pi over 2 and negative pi over 2, what's an antiderivative of sine? Negative cos. So if you evaluate, get rid of some of that curve, and I'll go over here. Actually, I guess I could make this bigger. You do get 0. Negative cos of pi over 2 minus negative cos of negative pi over 2. Lots of thinking required there, I guess. What's cosine of negative pi over 2? Both of these are 0, right? Negative 0 minus negative 0. 0, right? Or is it what? Plus or minus 0. Plus or minus 0. This is going to give you, what is that going to give you? To think about the graph of x cubed. If you know something about the graph of x cubed, it looks along those lines. If you do from negative 1 here, you should get a negative number for this because this area is below here. Okay, it's going to give you a negative area. This is the only reason I put these things in. That's going to be the same as if you switch this, if you're thinking about it here. What integral with positive values here would that be the same as? Just by the symmetry of that x cubed graph. Yeah, from 0 up to 1, that would be the same. I don't know what it is when you work it out, but I guess we could easily work it out as a 1. Well, this way, yeah, is this negative 1 here? Oh, negative a quarter because we have... Why? Oh, because we're using a... this is my downfall. What value do we need to use if we're working this out? We need to use an antiderivative of this. Yeah, 1/4 x to the 4th. I seem to always forget that I have to actually use an antiderivative, and I use this value. So that works out, right? What do you predict this is going to be then? You predict that this one is going to be what? This is going to be 0 because of the symmetry, right? If you have an odd function and you go from negative a to a, it should be 0, right? If you have an odd function. If you have an even function, it should be twice the value. Yeah, if you have an even function, if you know the integral from 0 to a, then the integral from negative a to a should be twice that much. This is really bad mathematical notation, but integral from 0 to a of f of x dx. If that equals some value here, let's make up a number. Well, I was just gonna put something like m. This should be then what? From negative a to a, that should be 2m, right? It should be twice as much. Okay. Now I think it's going to help if you have the calculator to be able to check these things, like with any one of those calculator functions. Just to get a sense of visually what you're doing. Don't lose track of what you're doing when you're evaluating things analytically here, with these kind of expressions. Don't lose track of what it actually means on a graph, okay, as we work through this. Integral from 1 to 1, we should have a sense of what some of these things mean here. Integral from 1 to 1, what's that going to be equal to? From 1 to 1, it should be 0, right? There's no, it doesn't, the x value is not any different, right? From 2 to 0, you could try doing that and putting those boundaries on the calculator, but think about what that means. That means if you have x squared, there's x squared. I know in a lot of real things, when this represents time, this wouldn't work. You can't go back in time from 2 to 0. But if we're counting down, I don't know. If the area from here to here was positive, right? If the area going from 0 to 2 was positive, what's the area going to be going backwards like that? Should be negative, right? And that makes sense when you evaluate it. If you use an antiderivative here of that, 1/3 x cubed, if you evaluate it 2 minus 0, you get a positive number. You get 8/3 or something like that, right? And then, so if you flip it around, 1/3 x cubed, 0 to 2, you get negative 8/3. This is going to be the net change in something. Like we looked at, right off the bat, we looked at the area underneath was the net change in whatever the quantity is. If you went back in time, if going forward in time gains you distance, going back in time you'd lose distance, right? So that kind of makes sense, even though it's impossible. That is a lot of arrows. Too many arrows. I don't know if we need to do this because you could actually summarize this. This is just with B's and A's and things like that. Area above the axis, area below the axis. If it's above and below, maybe draw a little picture for yourself. Put an A here and a B here, and then just draw some random function. Draw this one. I didn't really draw the x-axis in a good place, but draw it so it's below. Draw this one so it's above and below. Think about what this might mean. Think about what this is. Okay, we'll take a couple minutes to do that. Works out well. We're almost at 10 minutes anyways. We'll pause. What are we thinking here?
I think it goes up, and then when it hits the...
If you have your function here, well, if you have A to B here, I mean, when you draw the picture, it's obvious what this is the same as, right? If you have the area from A to B plus the area from B to C, if you add that together, what integral is that the same as? A to C, right? That's all you need. And then this is a 0, not a big circle. And then we've got to make sure those get in the video. And then the only other one here is if it's below, above and below, right? It's the net area. right? Where things above count as positive, right? That's positive. And this stuff down below here is negative. Okay? Now your coloring's a lot better than mine there, because you took the time to do it.
I did it. I had a really
10 minutes, panic.